Quantum physics, also known as quantum mechanics or quantum theory, is a fundamental branch of physics that deals with the behavior of particles at the smallest scales. It challenges our classical understanding of the universe, introducing concepts that defy intuition and reshape our perception of reality. At the heart of quantum physics is the idea that particles, such as electrons and photons, exhibit both wave-like and particle-like properties. This duality is encapsulated in the famous double-slit experiment where particles passing through two slits create an interference pattern on a screen, indicating wave behavior. However, when observed, they appear as individual particles, demonstrating their particle nature. This wave-particle duality is a cornerstone of quantum theory, challenging the classical view that particles and waves are distinct entities. Another fundamental concept is quantization. In quantum mechanics, certain properties like energy are quantized, meaning they can only take on discrete values. This is evident in the structure of atoms, where electrons occupy specific energy levels. When an electron transitions between levels, it absorbs or emits a photon with energy corresponding to the difference between the levels. This quantization explains phenomena such as atomic spectra and the stability of atoms. Quantum superposition is another key principle, stating that a particle can exist in multiple states simultaneously. This is famously illustrated by Schrödinger's cat thought experiment, where a cat in a sealed box is simultaneously alive and dead until observed. Superposition underlies many quantum phenomena, including the behavior of electrons in atoms and the operation of quantum computers. Quantum computers leverage superposition to perform computations exponentially faster than classical computers for certain problems. Entanglement, described by Einstein as spooky action at a distance, is a phenomenon where particles become correlated in such a way that the state of one particle instantly influences the state of another regardless of the distance separating them. Entanglement has been experimentally confirmed and is a fundamental resource for quantum communication and cryptography. It enables quantum teleportation, where the state of a particle is transferred to another distant particle without physically moving the particle itself. The probabilistic nature of quantum mechanics is encapsulated in the wave function, a mathematical description of the quantum state of a system. The wave function provides the probabilities of finding a particle in various positions or states. This probabilistic interpretation, introduced by Max Born, departs from the deterministic nature of classical physics. It implies that the outcome of a quantum measurement cannot be predicted with certainty, only the likelihood of different outcomes. Heisenberg's uncertainty principle further challenges classical notions, stating that certain pairs of properties like position and momentum cannot be simultaneously measured with arbitrary precision. The more precisely one property is known, the less precisely the other can be known. This principle reflects the inherent limitations in our ability to measure quantum systems and has profound implications for our understanding of reality. Quantum physics has led to revolutionary technologies and insights. The development of the laser, semiconductor devices, and magnetic resonance imaging, MRI, are direct applications of quantum principles. Quantum mechanics also provides the foundation for understanding chemical bonding, the behavior of materials, and the mechanisms of biological processes at the molecular level. Despite its successes, quantum mechanics remains an incomplete theory. The quest to reconcile it with general relativity, the theory of gravitation, has led to the search for a theory of quantum gravity. Concepts such as string theory and loop quantum gravity aim to unify these fundamental forces, though a complete theory remains elusive. In summary, quantum physics has profoundly altered our understanding of the universe. It reveals a world where particles can be waves, states can exist in superposition, and entanglement links distant particles. This counterintuitive framework has not only deepened our grasp of the microcosm, but also paved the way for groundbreaking technologies that shape our modern world.